Okay, so as in this section, we are trying to continue the discussions. We are already done with introductions of the predicate logic, and then we already discussed about what are the things that we have in predicate logic but not in propositional logic. Also, we already see how we can do the translation from verbal statement into predicate logic expressions, and then we continue with the negation structures for predicate logic, and then also we already see how a variable can be a bound variable or free variable. So now the next that we would like to see is how to prove the validity in a predicate logic. And as how it is mentioned in the previous video, difference with propositional logic, in predicate logic, the proof or the tool that we can use in this case is by doing proof sequence to prove the validity. It's look like it's impossible by trying to use truth table in order to prove the validity in the predicate logic structures. While in the propositional logic, that thing is still possible to prove the validity by using truth table. Okay, so before we start the process on how to do the proof sequence in the predicate logic, so let us see few things that we need to understand at the very beginning. Alright, so as we know, a valid argument for predicate logic need to be a tautology. So this is the same point as we see in a propositional logic. It must be tautology. It's just that in predicate logic structure, we not call it a tautology, but we call it as a valid argument. And then the meaning and the structures of the quantifiers and predicate determines the interpretations and the validity of the arguments. So here, the basic approach to prove the arguments, whether it is valid or not, is the same proof sequence methodology we use in propositional logic. So it will be the same rules, but beside we have 4 new rules we can tell. The first one is the 2 rules to strip the qualifiers. Is it 2 rules because we have for all, and also we have the existential, and then 2 rules to reinsert the qualifiers, because also we are having both for all and the existential in there. So that's why there are 4 rules, or we categorize into 2 new inference rule. One is to strip and the other one is to reinsert. Alright, so what kind of rules that we have? So as you see this one, you should already have this table on the paper that I already distribute for the complete rules for equivalence, inference, and deduction method. So as you see over here, the 4 rules is the one that highlight over here. Start number 1, number 2, number 3, and number 4 over here. So we have what we call as universal instantiation. We have existential instantiation. This one to strip out the qualifiers, and then the one to reinsert, which is universal generalization and existential generalizations. Okay, so in order you're not confused, you see the 3 over here is still using the variable, while the first 2 over here using the constants. but there are 4 in general. Okay, the rest of the rules, as you see here, is all the same. We have still modus ponens, we have modus tollens, we have conjunctions, we have simplifications, addition, hypothetical syllogism, disjunctive syllogism, exportations, inconsistency, distributive. So this is the same rules as we have for equivalence rules. And then also here we have commutative, associative, we have here commutative, and all the same thing that we have associative. We have the Morgant, we have implications, double negations, equivalence, contrapositions, and self-reference. So they are all the same rules as we have in the propositional logic. The fact that they should be the same one, it's just that we have the 4 new rules as mentioned earlier, due to the existence of the quantifiers in a predicate logic, which is universal and existential. And then this is also just another way to represent the rules that we have. So basically the difference between the proof sequence in the propositional logic and the proof sequence in the predicate logic is just about the existences of the 4 new rules to strip and to reinsert the qualifier. Okay, so now since we already know that, let's us just start with the first examples, how to do the proof sequence in the predicate logic. Okay, so let us have a predicate logic structures for all x, and then px implies qx, and this is 1, and pa implies here is qa. Okay, so this is the structures that we have. So still the same one, the proof sequence. First, definitely we need to list out all the hypotheses. So the first hypothesis will be for all x, we have px implies qx, and then the second hypothesis here we have pa. Now let me just explain first why exists the 4 new rules in the predicate logic proof sequence. Because if you see all the rules in the proof sequence, whether it is the inference rule or equivalence rule, we will not going to see any rules that have the quantifier inside. So there will be no rules that have the quantifier inside. So the existence is the 4 new rules, which is to strip out and to reinsert one, is actually for the qualifier. So as we see in this first hypothesis, we have this for all x. So in order we can find the match rules with this one, we need to strip out this qualifier first. So to strip out the qualifier is by using the universals instantiation. So you can check the rules later on, or let me just show it again here. The first one, so we have for all x px can derive pt, meaning we can derive to any constant. This one we call it universals instantiations. So by using these rules, then we are going to have, so universals instantiation on number 1. So instead of for all x px qx, then we have pa qa. Why pa qa? Because definitely we try to make it as what we need. Over here we have pa. If over here pt, then the one over here on the number 3 should be pt as well. So this is just to match between what we have and what we need. Okay, so that is for universal instantiations. So what next? So the next one, then we can check on the rules, which rules is match. So as we are going to look at these two now, then we can see that we have PA here, also PA here, and then that match this rule definitely is a modus ponens. Okay, definitely is a modus ponens for 2 and 3. So dismiss these two, then we can get QA. And there we go. The QA is the one that we are expecting in the final statement over here. Okay, of course this is a very simple examples. It's just to show it to you first, how we make use the 4 new rules in there, to strip and to strip out and then to reinsert back later on. Okay, let's just look at another examples. Let's see, now we have another structures for all x. We have px implies qx. Okay, and we have q y. Okay, not qy. Okay, implies not py. Okay, so how about this one? Again, the proof sequence. One, we list out all the hypotheses. So we have hypothesis first, definitely for all x, and then px implies qx, and then the second hypothesis we have not qy over here. Okay, so what we need to do the next one, now check immediately here whether we have quantifier or not, which is have on the first one. So we need to strip out this one by using ui for number 1. Then we have, since on the second one we have qy, so we can just make use the same one. So py implies qy. Okay, and number 4, now look at again, we have here not qy and qy. So what rules that match these two structures? Definitely this is modus tollens. So we can make use modus tollens for number 2 and number 3. Then definitely we are going to have not py. It's done. So this is exactly what we need on the final statement. All right. Okay, so sorry because someone just came in. That's one. Earlier it's just the same, but we have implement we implement ui and modus ponens. Over here we implement ui and modest tolerance. So in these two examples, we already demonstrate on how we use the new rules, universal instantiations, to strip out the quantifier. On the next examples, I'm going to demonstrate on how we can strip out the qualifier and then to reinsert again. Okay, now this is the structures that we have. For all x, px implies there is x px. Okay, so proof sequence, this definitely quite simple. First, list of hypotheses, definitely we have for all x px. Then we don't have another hypothesis here. The fact is direct to the conclusions, but just that there are different type of qualifiers or quantifiers. So first, we need to strip out the qualifiers here, definitely by using ui or number 1. Then we will have px. That's all. Now look at the final statement. It's also px, but with another qualifier which is existential. So in this case, we need to reinsert. To reinsert, what rules do we have? To reinsert, we have rule here. Let me just use red. We have UG, universal generalization, or EG, extensional generalizations. So to strip out, we have UI, universal instantiation, and EI, existential instantiation. But to reinsert back, we have universal generalization and existential generalizations. So since here what we need is existential, so definitely the rules will be EG of 2, which is existential generalizations. So we are going to have, that is x px. That's all. So this is exactly what we need in the final statement there. Okay, so the first one, from here to this, we strip out. This is what we call, we strip out the qualifier, because we have for all x, so to strip out we use ui. But from here to the final statement here, we call it to reinsert. So to reinsert, there is x, then we use eg, like that. Okay, so that is done for that one. But in case later on we have to strip out ex, then we use ei. And if we have if we would like to reinsert universals, then we use ui. UG. Okay. Reinsert using generalizations, strip out using instantiations, like that. Okay. So try to understand these 4 examples first, and then if all okay, then I'm going to provide another example which is more complex than this one, and we try to do the proof sequence. So that will be on the next video. Alright, thank you.